to our online NPTEL course Environmental Chemistry and Microbiology. I am Professor Anjali Pal from Civil Engineering Department. I am covering the environmental chemistry part. This is my second lecture and I am covering the acids, bases and salts. Today I will tell about the pH concept and the strengths of acids and bases, the hydrolysis of salts, what is the pH upon hydrolysis of salts we will get in the solution. We all know that there are different types of acids, bases and salts. Some of the acids are shown here HCl, HNO3, H2SO4, acetic acid, carbonic acid, phosphoric acid. Then some bases are also shown NaOH, KOH, calcium hydroxide, ammonium hydroxide, aniline, this is organic base, and salts like sodium chloride, sodium sulphate, sodium carbonate, sodium dihydrogen phosphate, disodium hydrogen phosphate, ammonium chloride, sodium acetate, ammonium acetate. So, there are different types of acids, bases and salts. Some are weak, some are strong, some are inorganic, some are organic. So, we will discuss about those. Before going to acids and bases, the strengths, we must know what is the pH. In aqueous solution, the concentration of hydronium ion, I already explained in my first lecture what is hydronium ion, that can range from 1 molar to 10 to the power minus 14 molar. It is convenient to express this large range by some logarithmic scale, and there comes the pH scale. We know that pH is nothing but log of hydronium ion concentration. Pure water at 25 degrees centigrade. Why the temperature is important? Because we all know that the equilibrium constant depends on the temperature, and I will show you the different values at values of the equilibrium constant of water dissociation, and you will see that how it varies from temperature to temperature. Now, but at 25 degrees centigrade, the H3O plus concentration for pure water is nothing but 1 into 10 to the power minus 7 molar, and pH therefore is 7. Similarly, 0.1 molar solution of HCl has H3O plus is equal to 0.10 m. So, pH will be 1 log 10 to the minus log of 10 to the base 1.0 into 10 to the power minus 1, that is 1. So, pH is nothing but minus log of H plus ion concentration or hydronium ion concentration. Similarly, pOH is nothing but minus log of OH minus ion concentration. So, 0.1 molar solution of NaOH must have a pOH is 1. Since pH plus pOH is nothing but pKW, so pH plus pOH is 14. So, if we can calculate the pH of this NaOH solution, pH of 0.1 molar solution of NaOH is 14 minus 1, that is 13. So, this is the concept of pH and pOH. This is very, very important. The most commonly obtained H3O plus concentration is below 1 molar. So, the pH is positive in most cases. In very rare cases it may be negative also, and the pH can go little above 14, but in general way we can tell that pH scale is 0 to 14, and we know that pH signifies the low concentration of H3O plus and vice versa, and change in pH by 1 unit implies a change in the concentration of H3O plus and OH minus by a factor of 10. And we can easily say that for neutral solution the pH is 7, for acidic solution the pH is below 7, and for alkaline solution or basic solution pH is above 7. The pH of a solution is directly measured using a pH meter, which is an instrument, very simple portable instrument also we can use, which is an instrument made in such a way that the sample solution is made a part of an electrochemical cell that has an output voltage which is sensitive to the H3 plus ion concentration. We all have seen the pH meter, a very simple instrument, and to measure the pH is also very easy. Now, ion product of water, I have already told in my first lecture what is ion product of water. We know from the Bronsted-Lowry theory of conjugate acid base pair theory, we know that water can act as an acid when it can give H plus ion and OH minus ion, which is nothing but its conjugate base. This is the pair, acid 1 and base 1 is a pair, and water can act as a base also because it is amphoteric character. So, it can act as a base also when it takes up the proton to form the hydronium ion. So, this is the conjugate acid base pair. Now, combining these two, we can write that this equation, which is nothing but the auto ionization of water. It proceeds, this ionization proceeds in slight extent under ordinary conditions, but it always happens. This is very, very important to remember. It always happens, and it is responsible for a small but measurable presence of hydronium ion and hydroxide ion. Even in the purest form of water, we will see that it is slightly dissociated and it forms the H3 plus ion and OH minus ion. So, Kw, which is the equilibrium constant of that reaction, is can be written as Kw equals to H plus ion concentration into OH minus ion concentration, or this is the simple way to write, but actually we should write Kw is equals to H3O plus concentration into OH minus concentration, which is nothing but 1 into 10 to the power minus 14 at 25 degrees centigrade. This is most important, and Kw is called the ion product of water. Because water is electrically neutral, that means H3O plus concentration is same as the OH minus ion concentration, and this is nothing but 10 to the power minus 7, and pKw is 14. Now, I will show you some seesaw. So, in satisfying the equilibrium, the numerical values of H plus and OH minus ion concentrations include all the H plus and OH minus ions present. It is true not only for water, but if something is there in the water, then also we must remember that H plus ion concentration and OH minus ion concentration, the product of these two will be nothing but 10 to the power minus 14. This is very, very important, and when H plus ion concentrations become higher, OH minus ion concentration must go to a low value. Okay. This is just like a seesaw. We know the seesaw, we all played seesaw in our childhood days. Some persons sits here, some child sits here and another child sits here. So, sometimes it goes down, sometimes it goes up, then it goes up, it goes down, then this goes up. So, but you can see the scale here, this is 1 and this is 10 to the minus 14. If OH minus ion concentration is 1, then H plus ion concentration must be 10 to the power minus 14. And here it is also shown that the values you know differs at different temperatures. So, for example, the value of Kw you see at 0 degree centigrade it is 0.114 into 10 to the power minus 14, whereas 20 degree it is 0.681 into 10 to the minus 14 and at 60 degree 9.61 into 10 to the minus 14. So, almost 10-fold difference you can see here between 0 degree and 60 degree, the values of Kw you see much different. Now, ionizations of acids and bases. If you remember the Arrhenius concept, the electrolytic dissociation theory, he first has observed that different things when put in solution, then they give different conductance. That means, the acid may be strong or it may be weak. This is not only true for acids, but it is true for bases also. So, there are some strong acids and there are some weak acids. Those which are strong, they are called strong electrolyte, which are weak, they are called weak electrolyte. And depending on the degree of dissociation, the acidity will come differently in the solution. All strong acids and bases are considered to approach 100% ionization in dilute solution. So, strong acids will be 100% dissociated. Say for example, HCl. If you put some HCl in water, then HCl will be completely dissociated. But if you put say for example, acetic acid in water, small amount of acetic acid in water, then it will not dissociate 100%. Only very slightly it will dissociate, and so it is called the weak acid or weak electrolyte. Weak acids and bases, however, are so poorly ionized that in most cases it is impractical to express the degree of ionization as a percentage. Now, here as the example I have shown a monoprotic acid. It is shown that say for example, this is the acetic acid CH3COOH, and then in that case if it is acetic acid, then and because it is not 100% dissociated. So, we must consider the equilibrium constant, which is usually expressed as Ka. This is the acid, that is why A is coming, and from this equation we can easily tell that Ka is nothing but H plus ion concentration into acetate ion concentration by the undissociated acetic acid concentration. Now, here also just like the H plus ion concentration and the pH, here also the Ka value and pKa value similar way it is related. What is pKa? pKa is nothing but minus log of Ka. So, if Ka is in terms of 10 to the minus 5, then pKa will come in terms of 4 point something. For acetic acid it is 4.74, for formic acid because it is stronger than the acetic acid. So, it is coming 3.74 at 25 degree centigrade. So, you can see here which is stronger, the pKa value will be less. In this case you see formic acid is stronger than the acetic acid, that is why pKa value is lower than the than the pK value of acetic acid. Similarly, for a typical base which is weak base ammonium hydroxide, we can tell that ammonium hydroxide can be dissociated as NH4 plus OH minus. So, Kb here in case of acid we write Ka, but here we will write Kb because it is a base. So, Kb for ammonium hydroxide is expressed as ammonium ion concentration into OH minus ion concentration by undissociated ammonia concentration. At this is very strange, very interesting for me that pKa of acetic acid is 4.74 and pKb of ammonia is also 4.74. Some nice example I will show you in later slides that this actually for me it is very interesting, I will tell you later. Now, strengths of acids and bases. Strengths of acids and bases depend upon the nature of the solvent. I already told you the Arrhenius concept, I already told you the Franklin concept. So, acid and base the nature will depend on the solvent. Okay. How it is acidic, how much it is acidic, whether it is acid or not, everything will be decided by the solvent. All acids are stronger than the all acids that are stronger than the hydronium ion appear to be equally strong in water. This is called leveling effect of water. So, HCl, HNO3 and then perchloric acid is everything will be same. This is called the leveling effect in water, okay, because all of them are stronger than the hydronium ion. That is why it is called leveling effect of water. Everything it is leveled off by the water molecule, water. In a solvent like ammonia which is stronger base than water, weak acids like acetic acid appear as strong as HCl. That means, we know in the previous slide also I have explained that acetic acid is a weak acid because it is weak electrolyte, it will not dissociate 100%, but if you take instead of water, if you take ammonia as a solvent, then in that solvent the acetic acid will act as a strong acid just like HCl in water, as because there is a cent percent transfer of proton to the solvent, very interesting. And say for example, if you take ammonia, acetic acid will be acting as a strong base. Okay. Not only ammonia, pyridine, aniline, they are also organic bases, they are also acetic acid will be acting as a strong acid. But in the similarly all bases like which are stronger than the hydroxide ion appear equally strong in the water due to the leveling effect. This is just the opposite, leveling effect of water. In a solvent more acidic than water, that is glacial acetic acid, weak bases like ammonia or pyridine or aniline, this is nothing but aniline. So, aniline is a weak base, so it is not completely dissociated, but if you take acetic acid as a solvent, then it will be acting as a strong base. So, this tells that strengths of acids and bases depends on the solvent. Okay. So, acidic solvents like acetic acid, formic acid etc., are suitable media for this is the application part. So, if you want to, I will tell you later part the how the titration between different types of acids and bases can be done, what should be the indicator used. But here just remember this, that in acidic solvents like acetic acid, formic acid etc., could be very suitable, could be used as a suitable media for titrating weak bases, because weak base titration of weak base or weak acid is difficult. That is why you can make it strong, weak bases you can make strong base or weak acid you can make strong acid, if you can properly select the solvent. This is very interesting. Now, basicity of acid and acidity of base. The number of hydrogen atoms that one molecule of an acid can give to a base is known as basicity of an acid. Say for example, H2SO4 is a dibasic acid because 2 protons are there. HCl is a monobasic acid because there is only 1 hydrogen. Phosphoric acid, there are 3 hydrogens, so it is a tribasic acid. So, monobasic, other than the monobasic acid, everything like dibasic acid, tribasic acid, everything can be said as polybasic acid. Similarly, the number of hydrogen ions that one molecule of a base can accept from an acid is known as the acidity of a base. So, for example, NaOH monobasic, monoacidic base, then CaOH twice diacidic base, and aluminum hydroxide triacidic base. So, here also NaOH we can tell monoacidic base, but others we can tell that polyacidic base. Now, salts of hydrolysis of salts. Salts, there are many different, I have shown you initially that there are many different kinds of salts. How can we classify them? What is the way that we can classify them? Actually, there are two types of classification. In one type of classification, we can tell that salts can be divided in normal salts, acid salts and basic salts. And by definition, we can tell that NaCl, there is no replaceable hydrogen atoms or there is no replaceable OH group, that is why it is called normal salt. Here we can see that there is one hydrogen which can be replaced by any metal. So, it is acid salt or bisalt, and here there is one OH group which can be replaced. So, it is the basic salt. But there is another type of classification we can tell how depending on from which acid and which base they are produced. Say for example, some salts can be produced from strong acid and strong base. The good example is sodium chloride. So, it is a salt of strong acid and strong base. Now, there may be some salts like sodium acetate, where you can see that it is produced from acetic acid and sodium hydroxide. So, a weak acid acetic acid and strong base sodium hydroxide. There may be another type which is produced, example is ammonium chloride, which is produced from a weak base, that is nothing but ammonium hydroxide and a strong acid, that is the HCl. And lastly, the salt which is produced from a weak acid and a weak base, that is nothing but acetic acid and ammonium hydroxide. We all know that ammonium hydroxide is a weak base because it does not dissociate fully, and acetic acid is a weak acid, it does not dissociate fully. So, ammonium acetate or ammonium formate are the salts of produced from weak acid and a weak base. So, depending on how they are formed, when they are dissolved in water, then they will hydrolyze, and when they will hydrolyze, either they give acidic character to the water or basic character to the water or neutral character to the water. Now, how we will determine whether, how we will determine the pH when a salt is dissolved in water, that we can see here. Salts upon all salts will hydrolyze. Some salts can give acidic character, some salts can give basic character, that much I told. But what is the formula that we can apply? Say here, when the salt is coming from strong acid and strong base, example is NaCl, then if you put some NaCl in water, what should be the pH? It is neutral pH. But when you add some sodium acetate, which is coming from weak acid and strong base, which when you put some sodium acetate in the in water, then you will think that okay, it will be neutral pH, but it is not. It is not, because it is coming from strong base and weak acid. So, it will show the basic character in water. And what is the formula that you can use to determine the pH? That is nothing but pH is equals to half pKw. I already told you the pKw, what is pKw and what is the value of pKw at 25 degree centigrade, and half pKa plus half pKa plus half log C. What is C? C is the concentration of the salt, and pK is the, because it is the weak acid. So, you have to consider the K value and the pK value of that acid. So, pH is you can easily calculate using this formula. Similarly, if it is salt of weak base and strong acid, you will think, okay, ammonium chloride, if you dissolve, it will give neutral pH, but it is not. It will give some acidic pH to the water. And how can you calculate? This is nothing but pH is equals to half pKw minus half pKb minus half log C. Same way, C is the concentration of the salt, pKb, here it is ammonia, ammonia is the base. So, pKb of ammonium hydroxide you have to use here. And salt of weak acid and weak base, the example, one example is ammonium acetate, where you have to use the half pKw, pH is nothing but half pKw plus half pKa minus half pKb. Here both are weak acid and weak base. So, both the terms pKa and pKb are coming here. Now, depending on how much weak, but whether it is very weak or it is not that weak, depending on that the overall pH will depend. Okay. And depending on the base also, because these two terms are coming. So, depending on the strength of this weak acid and weak base, you have to calculate and you have to see what the pH of the solution is coming. This is also very interesting to me, because I have seen that if you use the ammonium formate and ammonium acetate, you will see in one case, in case of ammonium acetate, you will see that the pH is something, and in case of ammonium formate it is something. Something is more acidic, something is less acidic. Then I will show you how it is coming in other lectures. Thank you.